Hi, everyone. Welcome to the Project Volta session. This was previously known as the Android Power Performance Primer. If you could say that 3 times, 5 times as fast, there might be a prize in it for you guys. But this is the introduction to Project Volta. My name is Meghan. I'm a product manager on Android, and I have here with me Matthew.
I'm Matthew. I work on Android Cloud.
And we're here to talk about Project Volta. So we know that today, battery life is one of the biggest issues or biggest complaints that users have with Android devices out there, right? As we live in a world that's more and more mobile, it's really important that we have devices that last the full day at least, right? And I cannot tell you how many times I've been in a situation where after a long day at work, I'm trying to get a ride home, and I can't call a ride because my phone is out of battery. So we're really passionate about addressing this issue, and that was the impetus of Project Volta. With Project Volta, we looked at across the platform, Android platform, to see what opportunities lie there for improvement. We wanted to figure out what tools and APIs we could build for you guys to make it easier for you to make your applications more efficient, and also increase the transparency about power consumption for our users. So you saw some of the features that are more user-facing at the keynote from Dave. This session is going to focus specifically on the tools and APIs that we've built for you guys. So let's dig a little bit deeper into some of the analysis that we did. We started out looking at a Nexus 5, and we said, let's establish a baseline. We turned off everything on there, so it was in airplane mode, screen off, so completely in standby. And that gives you something like a month of battery life. But of course, we don't do this to our devices, right? We actually use them throughout the course of the day. We put them on cellular, we make calls, we have Wi-Fi, we have applications that are syncing, we are checking our social networks, we're playing games, the screen is on. Well, all of that adds up, and the battery life goes way, way down to less than a day. So that red line that you're seeing there, that's where we saw the opportunity, and we wanted to kind of dig even deeper into there and figure out what can we do there. So we decided to take a more microscopic look at what's happening. And before I go into more, let me talk about 3 active use cases that I'm going to talk about as we do this analysis, right? First, the application processor being awake, right? We know that when the application processor is awake, power is being consumed. Next, the cellular radio being awake. And we're going to look at what happens when that is awake and is doing its activity. And then finally, the screen being awake, right? That's one of the biggest drawers of power on the device. So we'll take a look at each of these. Again, first, let's establish ourselves a baseline, right? So what you're seeing here is current draw over time, right? So we basically hooked up an amp meter to the device to measure what's happening, what kind of power is being drawn by the device over time. So this baseline right here is in standby, that standby mode I just described, where the only thing that is really active is that the cellular radio is in its standby state, where it periodically checks in with the cell tower, right? And that's what these little spikes are. So this is our baseline. Very little power is being consumed. Let's say you wanted to turn the CPU on just for a brief period of time, right? And this is what happens. So we turn the application processor on. The processor turns on. It checks to see if there's any work to do or not. And then it goes off because there's nothing to do, right? This was a no-op. Well, just to do that much power is consumed. You can see that it's actually on for a little over a second. And what's happening is that the processor has to turn on, load all these things into its RAM and into its memory, and figure out what it needs to do if it doesn't need to do anything, and then it tears everything down, right? So that's consuming power. And you can think of the area underneath that curve, right, the integral. That is the power, the milliamp hours that are being consumed. Next, let's take a look at what happens when you want to send a packet over the LTE radio, right? So we decided to simulate sending 1 packet over LTE. And here's kind of the shape we saw. So it starts out in standby, and then we see these spikes. So the cellular radio is coming up, it sends the packet, it receives this acknowledgement, right? But then you see all these little spikes afterwards, right? So first you see a few big spikes, that's when the activity is happening, and then afterwards you see this long tail of little spikes. Well, what's happening there is that the radio decides that, hey, I just sent this packet, maybe there's more work to do. So I'm going to stay in this in-between state. I'm not completely in standby, but I'm ready just in case something comes up, right? Well, that seems reasonable. That makes a lot of sense. But if this happens a lot, right, that's extra energy that is spent, and the device is not actually doing anything useful. So we'll come back to that. I think there's some opportunity there. Let's quickly take a look at what happens when the screen turns on. There's a big spike, right? You would expect that because the screen is a huge, huge power consumer, right? One of the biggest ones because you have to turn on these LEDs and paint the screen and do the processing to figure out what to actually show on the screen. So turning the screen on for a second, this is what we saw as a curve for power consumption. Cool. So let's take a look at this in a different way, right? Let's compare that to that baseline that we saw. Let's assume that we wanted to do one of these active use cases for 1 second. So we took the power that that consumes and divided into it the standby power to figure out what are we trading off when we keep the device active for 1 second, right? And it turns out that we actually trade off 2 minutes of standby, right? This is a rough number across those 3 use cases. Obviously, you're going to be trading off more if the screen is on for 1 second. But let's say it's 2 minutes, right, for the sake of this. Well, or roughly 2 minutes. Do 2 minutes really matter, right? That seems like a really small amount of time. Well, if it was just once, right, just once this was happening, then yeah, it doesn't really matter. But let's take an example where you have 50 apps on a device, right? We have tons and tons of apps on our devices. They're syncing all the time. We're using those apps all the time. Let's say you had 50 apps on a device, and they were each keeping the processor or the cell radio or the screen on for 1 second every hour, each of them doing this. Well, that amounts to 100 minutes of standby time that you trade off every hour. You did this for 8 hours, that's 800 minutes. That's a lot of minutes.
That's huge.
It's huge, right?
Yeah.
So why can't apps just be lazier? Right? What if apps were just lazier?
I'm not sure, Meghan. That sounds kind of gimmicky. Could you explain this some more?
Yeah, sure, Matthew. Let me introduce a concept called lazy first, right? The idea here is that if your application can be lazy first, then be lazy first, right? The obvious way to do this, reduce the number of times that you keep the device active. That seems like a no-brainer, but of course that's not doable all the time. There's a lot of legitimate times when you need to be connecting to the network or keeping a wake clock. So maybe you can coalesce a lot of these activities, right? If you have a lot of network calls in succession, you can group them together into one call so you pay less of that overhead that we just talked about. Now finally, you can defer it, right? If you have content that needs to be updated to the application every week, it doesn't need to happen right away. It can happen. You can defer it to maybe when the phone is charged or plugged in, right? That's what I mean by lazy first, Matthew.
OK, so I mean, I guess when you put it in that context, this makes a lot of sense, right? On mobile, we have these devices which are constantly transitioning states. So it's a quite likely scenario that you're going to be in a situation where it's expensive to do certain types of operations. But if you can wait for long enough, like, and that's the key of the matter, like this waiting, you're most likely going to get into a situation where the environment is much more cost effective. So essentially, the thing we'd like you to ask yourself is, what is the longest amount of time that I'm willing to do this type of thing? And then you can schedule this work based on that. Right? But this is kind of a big ask, because the infrastructure up until now just hasn't really existed. But that's changed in L. So we built out a new set of APIs, which we're calling the JobScheduler, which make it really easy to specify these types of constraints that directly target the types of work that you're interested in, and then provide a callback for the system to know where in your application this logic should be run. So I'm talking about jobs and work, but what exactly do I mean? For example, like a non-user-facing network call. So this is a case where the users interact with the application, and you have some data to upload, and they're not expecting any sort of callback. They're not expecting to see any change in the UI. So yeah, you could upload this immediately, but if the user isn't expecting to see anything from this, why not wait? Why not defer this operation? Another example that we could think about is any sort of CPU-intensive operation. This is like video processing. This is database cleanup. Again, non-user-facing, really easy to defer if the infrastructure did exist. So just another example, any sort of job you want to perform periodically, like some sort of cron job or something that you'd like to happen at some point in time in the future. So let's take a look at a specific example. Every 15 hours, perform some database cleanup and maybe upload some logs to my server. So at this point, you might, this probably looks like a common situation that a lot of you all have done and have had to do on a regular basis. And you're wondering, well, why is the Android team gone to all the trouble of building out this brand new API for something that's been possible since the inception of Android? But then again, if you've done this before, you probably agree with me that it's not that simple, right? So in the first place, you want something to happen in about 15 hours, so you set up an alarm with the alarm manager. That's fine, that's pretty simple and well understood, but the alarm manager doesn't persist these operations. So you're gonna probably have to write some stuff to storage. And at this point, all you're really interested in is a wall clock time, plus whatever parameters you were interested in the first place that you need to do this work. But 15 hours passes, the alarm manager sends you your broadcast, your app wakes up, and it tries to hit the network, and there's no connectivity. So at this point, you register with the connectivity manager to let you know that when connectivity comes back. But we're on mobile, and these environments are constantly changing, right? Your network could be flapping, your server could be down, or like there could be all sorts of failure scenarios. So you go into like a failure state, you're doing your own back off, you set up some more alarms with the alarm manager, you have to track this, this failure, you have to write all these parameters down into storage because you're using the alarm manager, and if the device reboots, all of this stuff will go away. So it's really not that simple. But let's take a look at how we do this with something like the job scheduler. So again, you're seeing here that we're providing you this builder, and that which you use to produce these job info objects. And a job info is an exact encapsulation of what it is that you'd like to do. So in the constructor, you provide a job ID, which is some integer that you assign for the job yourself, which you use to differentiate this job from other jobs that you might schedule against the system. And then you give it this service components. And this is the service that you subclass that we provide where your execution logic is housed. And we'll talk about that some more later. In this case, we're asking for any sort of network. But if you know you have a bunch of uploads to do and you want an unmetered network, you can also ask for that type of thing. Then you're setting the timing constraints. In this case, I want this to periodically happen every 15 hours. And then you're asking that the device be plugged in. And that's it. There you have it. All right, so we saw a bunch of, this example has a lot of interesting criteria. But this kind of just scratches the surface of the types of things you can do with the job scheduler. Let's look at some of the other things. Let's look at it all in total. So the first thing that we've introduced in L, and this is brand new, is this network activity awareness. Now this is actually a connectivity manager API that we've integrated against. So you can use this in your applications if you wanted to do your own stuff. But for our purposes, and this is getting back to that graph you saw earlier that Meghan showed, with that really long kind of tail where the network was not quite, was not quite idle, but wasn't quite active either. So if we're aware that the radio card is in that state, we can piggyback on that and take advantage of that opportunity. The next thing we introduce is idle mode. So this is, as it sounds like, a period of time for which the system has determined that the phone is not being used and is not likely to be used anytime soon. So just to take an example, if you set up a job that required idle mode and also charging, this would probably be executed sometime at night when the user is sleeping and the phone is plugged into the wall on their bedside table next to them. And from a battery perspective, I mean, you can't do much better than that. You can hammer the CPU, you can do whatever you want. The user isn't around to see any of this stuff. And when they wake up in the morning, the battery's at 100% because it was plugged in all night. We've also consolidated a bunch of pre-existing functionality. We saw this in the previous example. You can ask for tasks to run while the device is charging, and you can also specify different types of network. So these are the types of powerful criteria that you can specify. But let's talk a bit about the features. So as I mentioned, the job scheduler, you don't have to worry about persistence at all. You can specify your execution state. You hand a bundle of parameters to the system, to the job scheduler, and we take care of that for you. We hand that back to you at execution time, no matter how often the device may have rebooted in the interim. And then you can specify on a per job basis your back off and retry criteria. And I think this is particularly powerful because you can say, for example, whether you want this back off to be linear, whether you want it to be exponential, and you also specify the initial back off time. So you can decide for yourself how you want your job to behave when it gets into a failure state. And finally, you set up these timing criteria. You can ask for things to happen once, at one point in the future, or just reoccur periodically. So because examples are fun, let's take a look at another one. And this one is going to look more at the timing side of things rather than the other one. So again, we're using some integer job ID, which we've incremented by 1, in this case, because we used some integer in the last example. Same, this is providing endpoint to the server, to the job scheduler. But here we're saying that I don't want this to run until 5 seconds has passed. So only after 5 seconds will this be eligible for execution. And this is an interesting setup. In this case, we're we're overriding with a deadline. So we're saying in 15 minutes, come what may, this task has to run. So, for example, you would think that if we asked the network, but 15 minutes passed and there wasn't a network because the phone is in airplane mode or there just was nothing available, you would be run anyway. So this is a guarantee for you guys to know that your job will occur by a certain point. But I mean, bearing in mind that if you set this deadline, and it's your responsibility to check in your code that the device is charging or that the network is connected. Right? So that's an example, and we've seen so far how you build these objects, a bunch of the different criteria, the functionality you get, and how you hand them to the job scheduler. Let's talk a bit about how you execute your logic. This is pretty simple. The system, when it's determined that your job is eligible to run, will just call on start job in your service. And the service in this case is a service that we provide. So you don't have to worry about any of the service lifecycle mechanisms or anything like that. You just override on start job, bearing in mind that this happens on the main thread of your application. So any work that you want to do, you have to offboard using any of the numerous framework components that let you do concurrent programming. You do your work, and you call job finished when you're done. But we set up a bunch of criteria that it's, for example, charging. And it might be the case that you're doing your work and the phone is unplugged. So the facility for that is that if this happens and the criteria that you set up are no longer valid, the system will call on stop job to let you know, hey, you need to wrap up whatever you're doing and stop doing your work. So yeah, that's it. I mean, I think it's a really powerful API. It's really simple to use. You just hand a lot of the complicated functionality to the scheduler, and you worry about what's important to you, right? Just executing your logic. But how do we actually measure that we've made some improvements?
That's an excellent question, Matthew, right? We talked about all these APIs and sort of some of the issues that we discovered earlier. Well, you start investing energy into building them. You want to be able to know that you're making a difference and you're actually improving the battery life. So one of the ways to do this is to literally hook up an amp meter to the battery leads, right? That's pretty much what we did when we came up with that chart earlier that you saw, those charts that showed current draw over time. This sounds pretty cool, but we did this in the lab with equipment. It's probably not practical for most of you out there. So we've improved the onboard battery stats, right? These are the things on device, information that's collected that's relevant to the power consumption on the device. So let's talk about that. This is the same set of information that is currently powering the battery settings page, where you can see which applications or system components are consuming what amount of power. But how do you get to this? There's a simple ADB command, dumps this battery stats, that dumps out the battery relevant information. The -- charge is just to make sure you get the data since the last time the device was fully charged. That way you reduce some of the noise and you get a nice clean discharge cycle into this data. You can also supply the package name, which will make sure that the data is restricted to your specific application. Otherwise, you'll get the global stats as well. So let's take a look at what you get when you type this command in. One of the things you get is the global stats, right? This is actually really interesting information. It's giving you a macro view over that discharge cycle about what happened, what consumed the power. So some of the things that are interesting here to us that when we look at these are like the partial wake lock time, right? If that time is really, really high, then you know that something was off. Something was keeping the processor awake way too long, and that was probably the culprit that you can go after, right? You can also see the total runtime. In addition to that, you can see things like the mobile radio being on, the packets that were received on the mobile radio versus Wi-Fi, and that can give you a sense of what the network activity was like during that discharge cycle. Okay. We've also added a brand new thing to this battery stats in L, something called the milliseconds per packet. This is actually quite interesting. What it's showing is the total number of packets sent by a particular UID, right? And the UID, again, for your application is, you can go look that up in DDMS. It's the same UID that's used here. It shows you the number of packets that your application sent and the time that it took. So you can see, for example, the first example here, UID-A, is extremely inefficient because it sent only 4 packets, but it took over 12 seconds to accomplish that. Right? Let's take a look at another example here. So UIDs B and C. So B, you can see that it sent 3,600 packets over 42 minutes, versus C sent about the same, 4,000 packets, but only over 2 minutes, right? So there's a huge difference there, and it tells you that one was far more efficient in transmitting that information than the other. Now, this could be for completely legitimate reasons, or it could be an area that you can investigate to figure out what was going on. Next, we have aggregated stats by UID. Again, that same UID I mentioned for your application package. Here you can see data that is specific to your application, similar things like mobile time used. An interesting thing here is the processor usage, processor wake lock usage. So if you recall, what happens when we talked about the CPU being awake, when you wake up the CPU, there's time spent to perform the actions that your application wants to perform, but then that also enables other applications to wake up and perform other actions. right? So those actions, right, that is allowing other applications to do things while you're holding that wake clock, that is now being blamed to your application by 50%. So 50% of that extra time is being blamed to your application. Then finally, there's battery history. This is really powerful. This is showing me every single battery-related event that happened over that discharge cycle. You can find this in a bug report. Just look for the dump of service battery stats header, and you can find this information. It's actually at the top of the battery stats. And here you can see things like when the mobile radio was up, when wake locks were being held, or when different wake reasons for the wake locks. And from this, you can determine unusual patterns of power consumption or system activity.
I don't know, Meghan, like just looking at this, I'm sure there's a lot of really like rich data, but there's way too many symbols and like complicated numbers and names. If there was some way to kind of make this more transparent to the user, I think it'd be much more useful.
You think so? All right, Matthew, just for you. We built a tool called Battery Historian. So like Matthew, I like visualizations as well, right? And when I looked at this bug report, it was actually crazy amounts of information. I tried to put the whole thing into here, but it was just way, way too long, right? And so to be able to consume all that information nicely, you need a nice visualization. And that's why we built Battery Historian. What it takes is it takes those battery stats and spits out a nice visualization. It's a Python script that builds an HTML visualization. So enough talking about this magical tool. Let's see what this produced. So Matthew was kind enough to donate one of his bug reports to analyze here. So let's look at some activity on his phone. This is showing just the first few hours of that discharge cycle, and you can see a lot of different rows here. So we're going to zoom into this, but each of these rectangles are representing when that activity was reported, for example. So let's actually take a closer look. We're going to zoom into that part of the. Let's do this. All right. So the first row there is the battery level. This is when the battery level was reported, right? And the system logs that. So you can see, for example, you hover over one of these rectangles, and you can see that the battery level reported was down to 93% at that point, right? Again, this is since the last time the device was fully charged, so you're expecting a discharge curve there. Let's take a look at this next row, top. Top means what was the application running at the top? What was the user actually using at that time? That's reported here, right? And so let's see what Matthew was doing in those big red rectangles. So that second rectangle looks like Matthew was using WhatsApp. That's cool, Matthew.
Yeah,
communicating on WhatsApp. You got friends. That's cool. Let's look at what else he was doing. This other big rectangle that you see there, he was using the dialer app. So maybe he was making a phone call. We'll find out. Let's see what happens. All right, we look at some of these other lines. That big green line, Wi-Fi was running. So he was on Wi-Fi the whole time. That's pretty cool. Next, let's look at this screen line. What's happening here? It's interesting. I can see already that the first two rectangles are correlated with the first two red rectangles up on the top, and it looks like the screen was on when he was using WhatsApp. That makes sense. Let's see what else is here. Phone and call. All right, looks like he was making a call. We were right that when the dialer was up top, he was actually in a phone call. So look at how easy that was for me to take that complicated battery stats history report and quickly identify the patterns of behavior and usage there. Now let's dig deeper into actually identifying some of the problem areas that we were talking about. So this other part of the report we can now zoom into. You can see things like wake locks being reported, when the system was running, things when mobile radio was on and off, and the reasons for the wake locks. And again, as I mentioned, hovering over these rectangles can give you more insight into what that entry is in the logs. So let's take a look at another bug report. Now, we decided to do a simulation. We looked at data, actual usage data from a whole bunch of our testers at Google. And based on the data from there, we created 50 simulated applications. And we wanted to see what happens, and we collected this bug report. So let's see what's going on here. I'm going to zoom in again in that bottom part. Looks like there's some activity there. Holy crap. All right. So there's a lot of rectangles there. It looks like there's a lot happening. All these applications are hyperactive. Hey, Matthew, do you think the paradigms of lazy first could be applied here? Maybe these things are legitimate, but maybe we could apply those paradigms here.
Yeah, so just Meghan, this looks like a primary candidate for the types of deferral and coalescing that we were talking about earlier. I mean, you see all these like gyrations, which basically mean that the phone is waking up, grabbing a wake clock, doing some really small amounts of work, and going back to sleep. And this is bad because you're paying that overhead of loading up the application processor every single time you see one of these spikes. And the same thing's happening with the mobile radio. And it's important to remember here that, again, we have that really expensive long tail of not quite idle, not quite active state. And we're paying that penalty every single time one of these little blocks ends. Because the mobile radio is coming up, you're using it, and it's going right back down. So as Meghan said, we got this data from a bunch of Google employees. So we have these 50 applications, and we simulated this traffic by using the alarm manager to just naively wake up the application and send some certain amount of network traffic, and then assume that it had finished its work and go back to sleep. So we decided to make these applications more lazy by adding a deferral of between 0 and 30 seconds. And we just randomly chose a number between 0 and 30 for each of these network calls for each of these applications. So I'm not saying that it's 30 seconds. I'm saying that on average, it's probably going to be about 15 seconds because this was a uniform random distribution. And we're going to get as many deferrals as 0 as we do 30. So 0 seconds of deferral being the active case where it just doesn't try to wait around at all. And let's see what we got. So immediately, even from a layman's perspective, the bottom table is much cleaner. Right? We don't have nearly as many wake-ups, which indicate that when the phone does wake up, you see the mobile network is active, so work is being done. And then it goes back to sleep at the end of that. And look at the shape of this mobile radio traffic at the bottom. Right? It's much more compact. There are much fewer of these boxes, so we're paying much less of this overhead penalty per mobile radio active transition. So I mean, I think this looks pretty good.
Matthew, that is amazing. This is amazing. So you were able to use the JobScheduler APIs to coalesce a lot of this activity, and we're paying less of that overhead penalty repeatedly that we talked about earlier. So I mean, these are just beautiful battery historian images, but what was the actual impact on battery life like? Yeah,
you're right. I mean, it's one thing to show like a nice picture, but the value that we're trying to quantify here is battery life. And so this simulation was ran over about 2 days. Both for the active alarm manager case and the kind of lazy job scheduler case. And in the former, we started at 100%, and it dropped down to about 55% battery life after 2 days. And in the latter, with the job scheduler, the drop was from 100 to about 70%. So that's a really remarkable difference. And I'm not making the statement that we're going to see this improvement in battery life across the board as soon as everybody jumps on board of these APIs. But it does give a kind of a ballpark estimate of the types of improvements we can make.
Yeah, but that's still really, really cool that you were able to get a 15 to 20% increase. Granted, this is a simulated use case, but that means that there's some real-world battery impact you could have for users. Yeah. So that's really cool. Now, Matthew, if I understood the simulation correctly, though, you weren't optimizing just the one app. You had to optimize all 50 of the apps. Is that right?
Yeah, so essentially what this simulation kind of comes like is that some deity, I jumped into a device, and I decided to manually, artificially make each network request lazy. And that just isn't the case, right? This is something that will affect everybody. Like, this is something we're thinking about in the framework. This is something that we're thinking about in Google Play Services. And this is also the kind of thing that affects all of you guys, the developers. Right? But the issue with it being a collective problem is that when we start making steps in the right direction, we can reap the collective rewards.
That's very eloquently put, Matthew. Thank you. He's exactly right? This is something that we all have to embrace and help address. And if I were to sum up this whole talk, right, we just tell you about procrastinating, right? We want you to build apps that procrastinate, that are lazy first. You can use the JobScheduler APIs to help do that in an efficient way and allow the platform to optimize how it helps utilize this underlying system resources in a power-efficient manner. And then finally, Battery Historian as a tool that can help you digest large amounts of battery-related statistics and see them visually in a nice timeline.
Yeah, man. That Battery Historian tool was excellent. But how do people actually use it? Because it's one thing to give a tool, to say the tool exists, and another thing to put it in the hands of developers.
That's actually a really good point. Battery Historian is a tool that we're open sourcing for all of you guys. Right? As I mentioned, it's a Python script. You can find it at that GitHub URL today. Keep in mind, though, it will work with battery statistics from the L preview build, which will be available tomorrow. So once you start running that build, you can gather the battery stats and start using Battery Historian to visualize those stats. Also, if you have any questions about what we just talked about, Project Volta, JobScheduler APIs, or Battery Historian, we have office hours for Project Volta from 3 to 4 p.m. today and tomorrow at the Android sandbox booth just right outside.
Yeah, and so we went over the job schedule in some detail, and there's also an IO Bytes video up on YouTube if you want to dig some more into this stuff. But if you're interested in just jumping straight into the code, we have a sample app up, which will let you set up these jobs. It gives you a really simple UI to specify the constraints that you're interested in and get the callback from the system. So that's up on GitHub at Google Samples, Android Job Scheduler.
And we started this talk by saying that we're passionate about battery life. This is not just something that we're passionate about in the Android framework, but across Google. And so, I'd encourage you to check out some of the other sessions, like the Achieving More with Mobile Cloud, where they're going to talk about some of the APIs that they're introducing and building to help make things more power efficient and make it easier for you guys to make your applications more power efficient as well.
Yeah, Meghan, thanks a lot, man. I thoroughly enjoyed that talk. I thought you were eloquent and well-spoken.
Thank you, Matt. Likewise, likewise. And thank you all for attending the session. We hope you enjoyed it as much as Matthew and I did. Now go out there and try out these APIs and Battery Story and let us know what you think.
Yeah, thanks.
Thank you.